see, yeah, it's worth recapping on what we did in the first talk. And so we talked about rates and ratios and proportions.
Yep.
And we talked about incidence and prevalence. We talked about the situations in which you'd use the word, the term incidence, and the situations in which you'd use the word prevalence, eh? And we gave some examples of that, like with rheumatic heart disease, where acute rheumatic fever would be the incidence of acute rheumatic fever, and the rheumatic heart disease that would be the prevalence, isn't it? Prevalence, because it's more a population-based measure. And the same with TB. We talked about, for some diseases that are where there's a large proportion of the people affected who don't actually come to health facilities, then it's important to know the prevalence as much as it is important to know the incidence. Yeah, but finding the prevalence can be even harder. So today, I just wanted to. We also yesterday talked about the steps to a research project, and we can address questions about that. But today, I wanted to talk about some basic statistics, and yesterday we talked about some metrics, and some summary metrics. So means, and today I want to talk about means and medians, and confidence intervals, and from that follows like what types of studies would you use these things in, and the first type of study I want to talk about today is a case control study, and many of the studies that we do are like observational. So all you're describing is the population. You're describing it in descriptive terms. But when we get to things like confidence intervals and odds ratios, then you're more talking about analytical statistics. So odds ratios are analytical statistics where you're trying to find associations between two different things, whereas means and medians are really just descriptive statistics, like proportions, rates, and ratios are descriptive statistics. Okay, does that make sense? Yeah. You're not comparing one subpopulation with another in descriptive statistics. You're simply describing the population, right? You could describe two populations, but you're not comparing them. So a way of comparing them is to look at odds ratios or relative risks or other things. I won't talk about relative risks today, but we will talk about means and medians and how they're different. It's a little bit like incidence and prevalence. You have to know when to use each one, right? So mostly we talk about, mostly we think about the mean as being the average point, isn't it? Eh? And I said yesterday as some of you were presenting your studies, that often the mean is appropriate for normally distributed data, all right? That is, that has a normal distribution. So you can think of a lot of different statistics that have a normal distribution. So can you give me one that has a normal distribution? Yeah, blood pressure in a general population, isn't it? Yeah, in the general population, blood pressure has a normal distribution. Height has adult height has a normal distribution in the general population, right? Weight has a normal distribution in the overall general population. If you're looking at a clinic population or a hospital population, often those things don't have a normal distribution because you've got more sick people, or there might be more overweight people, or there might be more undernourished people. So then there'll be more skewing of the data one way or the other, right? There might be more people who've got like a metabolic syndrome, so their blood sugar will be higher, whereas normally blood sugar has a normal distribution, yeah? So that's, but when you're looking at an overall population, then those common, like basic physiological variables usually have a normal distribution. Serum sodium has a normal distribution, yeah? But it won't necessarily in the children on the ward. There might be a skewed aspect to the serum sodium, yeah? There might be more hyponatremia or more hypernatremia, yeah? So you need to first, if you're going to use the mean, then you need to know whether your data are symmetrically distributed. And if in the problem with mean in most of the populations that we studied is that often there's some skewing. So low birth weight babies, they'll be clearly skewed, won't they? Yeah. they'll be skewed to being smaller, right? Or birth weight in a special care nursery, that will be skewed towards low birth weight rather than being normally distributed. I mean, at the other end, you might have a small number of babies who have birth asphyxia who are larger than normal. So you'll get some, it's not totally skewed, but often in a population of like newborns in a nursery, there'll be more low birth weight babies than will be babies with birth asphyxia. So therefore you'll have, you know, a longer tail of the smaller babies. Yeah. So in selected populations, like clinics and hospital wards and that sort of thing, it's rare to find normal distribution in too much, right? Now, but it's useful to know how to calculate the mean and how to calculate the median. That's what I really want to show you today. So you know how to calculate, I think you know how to calculate the mean, don't you? Huh? So I want you to try to calculate the mean of this this series of numbers. I think there's 11 numbers there. Okay, I'll write them on the board and we do it together, or you guys do it and see how you go. Probably do it with that. Okay. How do you calculate the mean?
The total sum.
The total, and divide that by
The individual, like the number of.
the number of measures, isn't it?
Yeah.
No, subjects, the number of measures. Yeah. So what was the total? What did you get as the total?
75.
75. And the number of measures were 11. Okay, so 75 it's 75 divided by 11. Yeah. And what's that? 6.8. Okay, 6.8. Yeah. I want to try to describe how it can be different if you have skewed data. All right. So this is 6.8, as you said. Let's calculate the mean if one number, one additional number, or maybe the last number is not 14, but it's 44. Right. So if the last number is 44, then calculate the so it's 105 divided by 11 still, yeah, and therefore the sorry 9.5, yeah, 9.5. Okay, so you can see that the addition of one number to one number that is an outlier, that's called an outlier, that can really skew the mean. All right. Okay, so that's the mean, right? Now the median is for non-normally distributed data. That makes sense from what I've said. When you've got symmetrically distributed data, then the mean and the median are very similar, right? But if you're comparing where groups where there's asymmetry, then the median should be reported. All right. And so try to calculate well, how do you calculate the median? Do you know the way to calculate the median? Highest and lowest, isn't it? Yeah, highest and lowest, and then it's the middle value. Yeah. So let's do that. These are not organized in highest to lowest. So what's we'll just go as 14 again. So what's the highest there? 14. And the next highest is 14. And the next highest is 12. And the next highest is 11. 8. 5. Yeah. 4. 2. And 1. And is the 1 there? It's 11, I think. Yeah, 11. Okay, I think that's right. So is that right? Yeah.
No 3.
Oh, there's no 3. Right. There's 2 twos.
3 2.
3 2. Okay. 2 2 2. Okay. Right.
And a 1.
And
a 1.
And a 1. Okay. So now all you do is cross off the, is that right? Yeah.
Yeah.
Cross off the top one, cross off the bottom one, cross off the next one, cross off this one. Yeah. And what you're left with is median. Does that make sense? Yeah. Okay. Now let's say that was 44, right? Instead of 14. Then what's the median? It's still the same, yeah? So when you've got very skewed data, then the median is consistent, right?
Yeah.
Because you're excluding the outliers. That's the main thing about it, right? So normally for the populations that we look at, you'll be looking at medians instead of means. Yeah. Okay. Right. Hope that makes sense. Yeah. Okay. All right. Okay. About that. Yeah. So now when you've got that's called the point estimate. Remember we said yesterday that when you're thinking about the metric that you're going to measure, then you've got a point estimate of your summary population, right? Whether it's you've got a population of children and you're trying to find the summary statistic for weight, right? It's in kilos and it's let's say the median, but it's a point estimate. Your median weight, if these were in kilograms, would be 5 kilos, right? But 5 kilos doesn't tell you anything about the spread of the population. Remember I said 5 kilos, that if it's a median, the range could be 6 to 7, or it could be like 1 to 9, right? And still the median would be 5. So when you're reporting your summary statistic on any variable, then you have to think about what the measure of spread is. Okay. And so when you're using the mean, as I said yesterday, when you're using the mean, then the measure of spread is the standard deviation. All right. And when this is like a normal distribution curve, and if your data are normally distributed, then there are some rules about what 1, 2, and 3 standard deviations are away from the mean, right? So 1 standard deviation, the mean plus or minus 1 standard deviation is always 68% of your observations, right? Yeah. And the mean plus or minus 2 standard deviations is like 95% of your observations, right? And so on either side, what is the percentage on either side of your observations? The outliers beyond 2 standard deviations. No, it's 2.5, isn't it? 2.5 one side and 2.5 the other side. Does that make sense? Yeah. Yeah. And so what we often say about a population is that 2 standard deviations below the mean or above the mean, that's the normal range, that so-called normal range. And so therefore you've got still 2.5% of people outside that are still within normal. They're in the normal limits, right? The same for, say, serum sodium. Like the serum sodium, the normal range is, what is it, 135 to 145. So the mean will be 140, right? But there'll still be 2.5% of the population that have their serum sodium a little bit lower or a little bit higher, right? Won't be a lot lower or a lot higher, but it'll just be a little bit, right? And that still can be within the normal range, like 134 or 146, yeah? And it could still be sort of within the normal range, right? Okay. But when you've got 3 standard deviations either side of the mean, then 99.7% of observations fall outside that. So therefore you've only got what percentage either side? Yeah, 0.3 or 0.15, isn't it? 0.15 either side. So it's a very, very small percentage, a minuscule number of normal will fall outside that, right? Does that make sense? So we don't usually call like plus or minus 3 standard deviations normal, right? That's way outside normal, okay? Whereas 2 standard deviations is normal. That's what a standard deviation is, and that's how we sort of use it, right? But mostly, as I said, we'll be using a median, and the measure of spread of this is called the interquartile range, interquartile, which means there's on either side, there are 2 quarters, right? So if there's 2 quarters, then either side of that, there's the median and a quarter one side and a quarter the other side. So therefore you've got 50%, it's the middle 50%, right? So either side of that, right, where you've got outside the interquartile range is like 25% on either side, right, of your population, right? Okay. And so often what we say is the median and the 75th to the 25th centile, all right, or the interquartile range, plus or minus 25% beyond the median, right? And that's the measure of spread, okay? Again, that's not affected by extreme values because if you've got a very extreme value, then that won't be included in your median and the interquartile range, right? Okay. So the main thing is if it's symmetrical, report the mean and the standard deviation. If it's asymmetrical, report the median and the interquartile range. And as I say, mostly it's useful to, like, it's a bit more precise if you can report the mean, but it's usually good enough and it's a better measure if you can report the median interquartile range if you've got skewed or non-normally distributed data. All right. Now I wanted to just cover the last measure of spread, and that's the Z-score, right? The Z-score is a bit like the standard deviation, right? Because if you think about weight on an overall population, like these charts represent the weights of thousands of children in at least 13 countries. I think the latest charts were based on thousands and thousands, like tens of thousands of children in 13 countries. So therefore, their weights are going to be normally distributed, right? And so it's valid then to use a measure of spread that involves the standard deviation, right? And the Z-score is a form of standard deviation. And the Z-score is the observed value minus the mean divided by the standard deviation. That's what a Z-score is, okay? Whatever you observe, the patient's weight minus the mean for that population, like that particular age, divided by the standard deviation, right? So there are programs that can tell you the Z-scores. You know, if you've got a column of weights, then it can tell you need the weight and you need the age, and then you can calculate the Z-score, and that's all it's doing. Observed value minus the mean divided by the standard deviation. And there's a calculation that will do that. Right. Okay. I won't get into that too much, except to, just I want you to be clear about the difference between means and medians and the difference between like the point estimate and the measure of spread, and how far all continuous variables, right? We talked about this a bit yesterday, binary variables where it's yes or no, then that's a 1 and a 0. And then all you're doing is looking at proportions, aren't you? You're looking at percentages of those that had the clinical sign or percentages of those that had the disease, right? Whereas for continuous variables, then you're usually looking at some statistic that's like a mean or a median, right? And the measure of spread being the interquartile range for the median and the standard deviation for the mean. Yeah, okay. I was going to talk now just briefly about types of studies. And so we've talked about descriptive statistics, both proportions, rates and ratios, and means and medians, and measures of spread. Let's now talk about some studies, and what we'll come to is how to do some analytical statistics that would enable you to do some of these studies. But just to go back on the types of studies that you can do, when you're probably familiar with this, but many some studies are simply like editorials, like it's not a study, but someone will write an editorial. It's like an opinion piece. That's what many people consider the lowest level of evidence, right? And then you can write up an interesting case that you've seen, right? And that can be useful. I don't think it's a non-useful thing. You can be useful because it might be a case that people haven't seen before, and it can be very helpful for clinicians to be able to read that case and to compare their case with your case, right? I tell you, actually, just last week, I had a very interesting case that only by looking for case reports could I find the answer. And it was a child who had, she came into hospital and she had all the signs of brain death, right? Very quickly, she had all the signs of brain death. And it was very strange because there was no clear injury or anything like that. She had cerebral palsy, but she just, like, she suddenly developed brain death. And I remembered something I'd read about baclofen, which is like an antispasmodic agent. And if a child takes a toxic dose of baclofen, or if they've got kidney failure, then their baclofen level will be very high. And the features are exactly like brain death. And there was only, in the literature, there's only about 4 case reports, one of which is in a child, and there's several in adults showing the same thing, right? And if you just wait for the baclofen to get out of their system, or you dialyze them to get the baclofen out, then they wake up. And that's what's happened to this girl. So it's really, there is value in case reports, right? There's no randomized trial of doing this, right? But sometimes when you're stuck with a difficult problem, you can look for case reports that are similar, right? Okay, so there's value in case reports. And then at least one of these studies that I could find was a small series of adults where someone had seen it more than once. And then they reported that they'd seen it twice or 3 times, and that they reported that in a case series. But most case series are much longer case series, right? And that can add strength to a case report, because if you see the same phenomenon many times, then writing up a case report on an unusual observation can be very helpful, right? Next is what we call ecological studies, which are usually just descriptive studies of a disease, right? That's not an ideal word, but it just means a descriptive study of a population. You might do like an ecological study of children who have pneumonia, trying to identify features within that population, or trying to describe their outcomes or the way they were treated. They're ecological studies because they're still observational, right? Then the next level, if you like, in this sort of so-called hierarchy, are case control studies. I'll talk quite a bit about them today, and then cohort studies, and we'll talk about them tomorrow. The cohort studies and case control studies are a bit different, and I'll try to explain the differences. And then there's randomized controlled trials. Now, once we get to randomized controlled trials, we're starting to get away from just observational studies, starting to get into some interventional studies, right? And they're not just interventional studies, they're comparative interventional studies, right? You can have interventions within cohorts, especially, and maybe in case control studies, but mostly if you want to know what the whether one intervention is more effective than another intervention, then you have to do something like a randomized trial, right? And then beyond that, even above that, some say, is like a meta-analysis. And what a meta means, like thinking overall, isn't it? Overall thinking. And a meta-analysis usually puts together a range of randomized trials on the same thing, right? So we won't talk too much about that, but you'll read various meta-analyses where there's 2, 3, 4, even more randomized trials, and putting them together, that can give you power of certainty, if you like, right? Because many randomized trials are relatively small, and in and of themselves, they don't tell you the answer. But if you put them all together, sometimes you can get closer to an answer. There's lots of problems, potential problems with doing that, because the trials are in different populations and that sort of thing, but it can be helpful. But today I just want to talk about, we'll get on to case control studies. I have talked about case reports. Remember, that's what you see as a clinician usually. And it can be, you can write a case report on some unexpected observation in one or a series of patients. As I said, the baclofen overdose question was very useful to find a few case studies on that, because it reinforced the idea that we should continue looking after this child rather than imagine that she was brain dead. it can, but it's useful because it can communicate an important clinical lesson. So if you've learned something from a case, then maybe other people will too. So writing it up as a case report can be very useful. On the other hand, a single case can be misleading because not always is like an exceptional case generalizable. Right? And so that's why we have to be careful in just putting too much store weight on an individual case report, because it's not, they're rarely telling you what the cause of a disease is. They're usually an observation rather than necessarily proving a cause. Right. So it can't, a case study or a case series can't identify associations or risk factors or cause. They just describe what you're seeing, right? Now I want to talk about case control studies, and they're done in an effort to try to do some analysis to find associations or potential causes, right? And so a case control study is when you've got a case series, but you also have a control group, and you're comparing the case series, usually a case series, a group of people with a disease or an outcome, and you're comparing that with a control group that does not have that disease, right? And you're looking for differences in exposure, perhaps, if you want to find an association between the exposure and the disease, right? If that's the purpose of your case control study, to look at like risk factors for a particular disease, then you'll choose a population who've got that disease and a population who don't have that disease, and look for differences between the two. And for that, it's appropriate to do what's called an odds ratio, right? Usually case control studies, not always, but often they're retrospective. They can be prospective, but they're often retrospective. And so, as I say, your case has to be defined. You have to have a careful definition of what your case is, like the disease has to be defined. And the controls are people who aren't similarly ill or don't die. And you compare the two, right? So usually they're retrospective, but not always, right? Now, the important thing about case control studies is the matching between the cases and the controls. If you get your matching right, then it's valid. But if your matching isn't right and it's not adequately matched, then it's often not valid to compare the populations, right? And when you're doing a case control study, you need to match the population on certain features. So often case control studies will be like matched on the basis of age, or even on date of birth, which sort of, that's the same, more or less the same thing, or on the place. Like you wouldn't want to have, have a control group that necessarily comes from a long distance away when you've got, say, a local disease you're looking at, yeah? They may be matched on the basis of other socio-demographic features like ethnicity, or maybe on socioeconomic issues that mean that the populations are largely similar, except for having that disease or not having that disease, right? The problem with that is that even though you try to match as best as you can, often there's unknown confounding as well as the known confounding. Confounding means something that exists in either the case population or the control population that means the outcomes of interest are not independent of that other measure. I'll explain what that means in a moment. But confounding is an important word to understand in case control studies and in cohort studies. Because they're often retrospective, not always, but when they're retrospective, there's a high probability of selection or measurement or recall bias, right? If you're, for example, looking at medical records for children who've got tuberculosis compared with children who don't have tuberculosis, and you're looking for, say, risk factors for tuberculosis in that population, then it depends on what's written down, right? It's the quality of the records that determine whether your your case control study is valid or not, because it might be that people didn't write it down with the understanding that it was going to be part of a precise study. So the medical records are not always precise, right? The case control studies are good for uncommon diseases, right? For an uncommon disease where if you look at a population over a long period of time, like you might not get a general population over a long period of time. You might not have too many people with that disease. But if you look at if you start with that population of children who've got that rare disease, then that's probably your best hope of finding any risk factors or associations. Right? Maybe that will become a bit clearer later on. The analytical statistic to look for associations that might help you understand causality is the odds ratio for a case control study. So we'll talk a bit about the odds ratio, and then I'll go back to a case control study, and hopefully that will illustrate a bit more about what that actually means. And I'll give a practical example of a case control study. Now, the odds ratio is like a measure of association, right? It's a measure of association. It's the number of events that happen divided by the number of non-events, right? So don't worry about the difference between the odds ratio and the relative risk, but usually for a case control study, we use the odds ratio, but it's the number of events that happen divided by the number of events that don't happen, right? Again, a practical example will help. And that's the odds, right? The odds ratio is the odds of being exposed to a certain risk factor if you have the disease, the odds of being exposed to a certain disease, to a risk factor if you have the disease, compared to the odds of being exposed if you don't have the disease. Again, so a practical example will help. Now, if the odds ratio is 1, right, then there's no association because your odds of being exposed was the same whether you had the disease or not had the disease, right? But if your odds ratio is much bigger than 1, then it means that you're more likely to get the disease if you're exposed to that particular variable, that particular exposure, right? If your odds ratio is much less than 1, then those with the disease were less likely to be exposed to that variable, right? Or that might even be a protective factor. It might protect you from the disease, right? Again, we'll get onto a practical example in a minute. Okay. Now, when we talk about odds ratios, again, that's a point estimate. It's a bit like a mean or a median. It's a point estimate, right? And so we have to have a measure of spread, a measure of not so much spread, but how confident are we that odds of being more than 1 is truly more than 1, right? And that's what's called the 95% confidence intervals. You'll have heard of that. It's like a measure of spread or a measure of our confidence, the spread of our confidence. Okay, that will be very confusing, I think, to you. So let's talk about a practical example. And I'm going to just go over a study that I did send around, but you might not have read it yet. But it's this is a good case control study that I think was done in PNG. Well, it's a long time ago now, 14 years ago, but it still stands up, I think, as a very good case control study. And as you know, we first got cholera in PNG in about 2009. Before that, there was no cholera for reasons that are a bit obscure, but there wasn't any. And it first came in Morobe province and in Madang, I think was, in 2009. And there were, in that outbreak of cholera, there was 15,000 cases, just mostly in those provinces. Many of you weren't around then, but there were lots of cholera then. And it spread up to the Highlands. There was a bit in the Highlands, but mostly in those 2 provinces. But 15,000 cases were reported, and the case fatality rate was 3.2% of all those 15,000. So a lot of people died of cholera. So this was a case control study that was done in Madang, I think it was between April and June in 2010. All right, and for this, you have to have, remember, you have to have a case definition for any case control study. So you have to rigidly adhere to a case definition because the cases have that definition and the controls don't have that definition, right? And so the case definition was a suspected case with Vibrio cholera isolated in stool. So there were obviously people who had severe acute watery diarrhea and they had Vibrio cholera identified in stool. So most of us would say that's a very good tight case definition, isn't it? It's not just saying a severe acute watery diarrhea. It's saying you have to have the bug in the stool. So you can be confident that those people, those cases actually had cholera, right? And the converse was that all those controls had to be free of acute watery diarrhea and Vibrio cholera in their stool. They didn't have cholera, right? Okay. The method was prospective. So again, a strength of this study that it was prospective and not retrospective. It was hospital-based, so it was based in Engau, actually, in Ley. And there were 3 controls per case, right? And sometimes when we do case control studies, we need to have more controls than cases, right? And that's because there's greater variability usually within your control group. And so you want it often gives you more power to detect associations or differences if you have more than one one control, 1-to-1, more than 1-to-1. You don't have to. Sometimes it's 1-to-1, but sometimes it'll be 1-to-2 or 1-to-3. Right now, the controls were children or patients that were admitted within 48 hours of a case, but they didn't have cholera, right? And the controls had either pneumonia or malaria. This is they weren't matched by age or any other thing. They were matched because they didn't have cholera and they had some other disease that brought them into hospital, right? So really, they weren't very well matched in terms of age or any of those gender or any of those things, but they were controls that were matched in terms of time. That's about it, in terms of time. Okay, right. Now, we're getting on to something a bit complicated now. So in this study, these were the risk factors they looked at, all right? And in this study, there were 54 cases and they chose 122 controls, not quite 3-to-1, but a bit more than 2-to-1, yeah? So they chose 122 controls and they identified 54 cases in that 3-month period. And when you've only got 54 cases, you can only look at a certain number of risk factors, right? You can't look at endless numbers. You can't look at 50 risk factors. And usually they say no more than 1 risk factor for every 5 cases, okay? So if you've got 54 cases, you can at most look at 10 or 11 risk factors, right? Some people say that's even a bit generous, and maybe if you've got 54 cases, you actually should look at a smaller number, like 1 to 10. 1 risk factor for every 10 cases. Yeah, for most studies it's like that, but this study they look probably around about 1 to 5. Okay, but so that means you've got to choose your risk factors very carefully. You can't just look randomly. You've got to have thought through what might be risk factors for the disease. Okay, you've got and ideally you've got to have thought that through before you start your study. Right? A lot of people think it through afterwards. And then they look at risk factors like age or quality of housing or whatever, and they're rather peripheral risk factors, right? So you should try to identify risk factors you think are quite, I suppose, likely ones, right? That you wouldn't be surprised if that one shows up as being positive. Okay, so they chose these risk factors over 20 years of age. Not sure why that, but I guess cholera often occurs in adults. Yeah, that resides in informal settlement, use the river as drinking water, defecates in open air or in the river, has soap at home for washing their hands. Now you'll see some of them look like they could be risk factors, and some of them look like they could be protective factors. Yeah, like hand washing at home, right? Choose betel nut. Well, again, I don't know the link between that, but they looked at that anyway as I guess a sort of social phenomenon. Washes hands before eating, knows a case of cholera, attends a funeral, right? Why might that be? Potential overcrowding or the mixing that you do during a funeral. Yeah, and certainly I'm not sure about for cholera, but for like Ebola, that was a very big risk factor, wasn't it? Going to a funeral, and of course more people died of Ebola than die of cholera in cholera outbreaks, but certainly for Ebola outbreaks in Africa, like going to a funeral typically of a person who died of Ebola during the epidemic was a very high risk factor. Not surprising, yeah? Knowing someone who traveled to a cholera area or shares a house with a diarrhea case, right? So they were the risk factors they chose to look at. And beside those risk factors are the number of people, both cases and controls, that had each of those characteristics. Does that make sense? The number, this N here, is the number that had that characteristic among cases, and the number that had that characteristic among controls. And this is the percentage of the people who are cases who were over 20 years of age, right? And so the percentage who had soap at home, 18 out of 54, so 33%. A third of people had soap at home. Does that make sense? Yeah. Okay. All right. Now, we'll just look at one of these things. That one risk factor, what I should say, when you're looking at a table like this, you can not cheat, but you can jump quickly to looking at, for example, the odds ratio and seeing which one has the highest odds ratio, because the one with the highest odds ratio might be the strongest association, right? And so the highest odds ratio, you look down this column of figures. Remember we said if it's much, much, much more than one, then it's likely to be a risk factor, right? Yeah. And so defecating in the open air or in a river had an odds ratio of 7.4, right? And that's because there were, of the cases, 24%, 24% had that characteristic, right? So it's a quarter. So not all of them, right? But only 4% of the controls. So the vast majority of the controls didn't do that. They had some other form of toileting, right? But those who were cases, a quarter of them had it, right? So it's not saying it has to be present in all the people, right? But it's a risk factor if the odds ratio is much, much, much greater than one, right? And when you look through this, you can see some that, like being over 20 years of age, you're more than twice as likely to have cholera as if you're under 20, right? What's another one? If you chew betel nut, well, that's not much higher, is it? It's not twice as likely, right? But it's a little bit higher, isn't it? Yeah, a bit higher, right? If you knew a case of cholera, it shouldn't surprise you that you're 4 times as likely to have cholera, right? Because it was 30% versus 9%, right? If you knew someone who traveled to a cholera area, then you're 5 times as likely. It's a bit like knowing a case of cholera, 87% versus 56%, right? So again, it's not saying that everyone who has cholera has all of these or any of these, right? But it's saying that these are risk factors because there's a big difference. The odds ratio is high. Okay. Now, so that's the odds ratio, right? It means your odds of having cholera were much higher if you did one of these things where the odds ratio is high. Can you see any of the variables where you might say, well, perhaps it's not a risk factor, but maybe it's protective? Yeah, washes hands before eating, right? And has soap at home, right? Yeah. So those two look like they might be protective factors, don't they? Because the odds ratio is much, much less than 1, right? Again, they're not surprising, but it's good to demonstrate that, right? That the odds ratio is much less than 1, right? So that's odds ratios for risk factors and odds ratios for protective factors. And now, remember we said we want to know, well, how confident are we? How likely do we think it is that those odds ratios are truly, remember the odds ratio is the point estimate, and we want to know some sort of measure of spread or confidence. It's more a measure of confidence that odds ratio is truly significant, right? And that's what the confidence interval is. And so you can see for the confidence interval for defecating in the open air, the confidence interval is 2.3 to 28, let's say 27.9, yeah? So what that means is that if a person defecates in the open air in those times, during that cholera outbreak, then they were 7 times more likely to develop cholera, right? But it could have been the true number that we're 95% confident about is somewhere between 2.3 times and 28% times, right? So the confidence interval in this case is very broad. It's very broad, isn't it? It's not a narrow confidence interval, but it's still even the lower limit of the confidence interval is much more than 1, right? At least it's twice as likely, but it might be even 28 times as likely, okay? Right? And therefore, this p-value at the end of it tells you how significant it is, right? But I think it's good to get used to like understanding the odds ratios and the confidence intervals, even more so than the p-value, because they give you a lot more information than a p-value, right? Often we focus on p-values, but actually the odds ratio and the confidence intervals are more instructive. The reason why the confidence intervals are so broad in this circumstance, does anyone know? It's because the numbers are quite small, right? You sometimes see case control studies that like have hundreds of patients in it, right? Or thousands of patients. And of course, in that case, your confidence will be much, the confidence intervals will be much more narrow. It's much more precise the more patients you get, right? But this is still a clearly significant result, even with relatively small numbers. But our confidence about whether the true number is 7 or it's somewhere between these two is quite broad. Does that make sense? Yeah, that's right. Now, so when you look at the confidence intervals, you can tell which ones are still significant. So being over 20 years of age, well, it was 1.2 to 5.2. So this is close to 1, isn't it? Yeah, but it's a bit more than 1. So there is an increased risk if you're an adult than compared with if you're a child. There's an increased risk if you're for informal settlement. It's a bit increased, but it might only be like a 40% increase. That 1.4 means 40%, doesn't it? Right? Because if it was 2, it'd be 100%, like doubling. Does that make sense?
Yes.
Yeah. Okay. But we might find one where, for example, yes, this one here, chewing betel nut. Well, it looked like it was 74% higher. Does that make sense? 1.74, right? It looked like it was 74% higher chance, but actually the true number could be like 0.68. So it overlaps 1, right? So it's therefore not significant. And you'll see if you move to that, then the p-value is 0.2. It's not significant, yeah? All right, because it overlaps 1, all right? Now let's look at having soap. Where's having soap, right? 0.2 to 0.87. So it's much lower than 1, isn't it? So therefore it proves that it's a protective factor, right? Because the upper limit doesn't overlap with 1, right? And when we get down to wash his hands before eating, well, it just gets to 1, doesn't it? Right? It just gets to 1. So you say in this circumstance, the study hasn't proved that it's protective, right? It's likely to be protective, right? But it hasn't proved it, mostly because it's a small sample size. Again, if you had a bigger sample size, then probably the confidence intervals would be much more narrow. Instead of 0.23 to 1, it might be like 0.3 to 0.6 or something like that. And then you know that that's with a larger sample size. Okay? So that's how you do that. Now, we've got down to here. The p-values just are a measure of the significance of the odds ratio, right? If it's less than 0.05, then we say it's significant, but you need to know what that means. The last thing on this table is what's called the adjusted odds ratio, right? Does anyone know what that means? The adjusted odds ratio. Yeah, it's adjusted. It's one variable adjusted for every other variable, right? And you don't worry about this too much at this stage, but like the analysis that on this side of the table, on the left side of the table, that's all what you call univariable analysis. You're only analyzing one variable, against the outcome of cholera, right? One variable, and then you're analyzing the next variable and the next variable. But there are ways of doing what we call a multivariable analysis, where you put one variable up against all the others, right? And that's what they've done here. And what that the reason to do that is because one variable might counter out the other one. And what you're looking for is the strongest risk factors, right? The strongest risk factors that are what we call independent risk factors. They're independent of all the other ones, right? Because you can see some of these risk factors are rather similar, aren't they? They're a bit similar, okay? So for example, washing your hands before eating and having soap at home, they're a bit similar. So they might counter each other out when you look in a multivariable analysis, right? Knowing a case of cholera or know someone who traveled to a cholera area, they might be similar and cancel each other out, right? But so sometimes it's useful to do this because at the end of the day, you want to know what the strongest variables are, right? Because then maybe they're the things that you can intervene on, right? Or you can modify the most, yeah? And when they did that, the variables that remained significant, right, were being a young adult, right, over 20 years of age, and defecating in open air, right? Because when you look at the 95% confidence intervals, it still doesn't get to 1, and that's, you know, adults compared with children, right? And that's and defecating in the open air 4.6. So it's come down a bit from 7.4, right? Well, again, because the sample size is small, but also because that's comparing it against the other ones. But it remains significant, right? Even in a multivariable analysis. Does that make sense? That's a bit complex, but you'll often see an adjusted odds ratio, and that's what that means. It's a multivariable analysis, okay? And you can see which ones were significant. Well, again, defecating in open air was. Having soap at home, again, is still significant. In fact, the adjusted odds ratio is a little bit less, 0.41, and the confidence intervals still show that it's a protective factor, right? And some after that, you know, knowing someone who traveled to a cholera area, that's still significant, isn't it? And that's probably cancelled out knowing a case of cholera, right? Because they're the same things, more or less the same, right? They're rather linked variables. Okay, I hope that makes sense. I just want to show you how you do an odds ratio calculation, right? There's some, you know, often we do it with computers, but it's useful to know how to do it. And we'll just do a little maths now, okay? Right. Remember, the odds ratio is the ratio of two odds, the odds of having the exposure if you've got the disease versus the odds of having the exposure if you don't have the disease, divided by, right? It's a ratio of two odds, right? Okay, so here's a 2x2 table that tells you a lot. So this is, we'll just use the open defecation one. I put the numbers in, right? And of the cases, well, I just went through the study, and of the cases, 13 defecated in the open air and 41 didn't, right? And of the controls, 5 did and 117 didn't, right? So that's a 2x2 table, okay? Cases, controls, had the exposure, didn't have the exposure, right? And then you say A, B, C, D, all right? They're the 4 squares, right? And it's the ratio of these two odds is A divided by B divided by C divided by D, all right? So remember in brackets, and yours do, remember odd mass, yours do the brackets first, yeah? Okay, so you're just looking at that. Yeah. Okay. Do you remember from like mathematics, how to divide fractions? Yep. You turn the other one upside down and multiply, right? I've skipped a step, but if you turn CD upside down and multiply it, you're going A times D and B times C. Yeah? Does that make sense? Yes. Yeah. You know that? High school maths. Yeah. Okay. So it works out like 13 times 117 divided by 41 times 5, and that's 1521 divided by 204, 205, and that comes out at 7.5. Does that make sense? Right, so that's how they do the odds ratio if you're doing it by hand, right? Obviously, most people do it usually with a computer, but it's useful to just know how you work out the odds ratio and what it means. And it's all odds ratios largely are 2x2 tables, right? Okay. Right. And again, when you're doing a study and you've worked out an odds ratio, or you've done any study and you found some statistics, some outcome, a lot of studies are written and there's so many statistics in it, but they haven't interpreted what they found. And I think it's really important that as part of your the results and the discussion, that you interpret your findings in plain language, right? Yeah, don't just leave it as statistics and p-values. Try to describe what you found in plain language. So you could say that people who had cholera had 7 times the odds of practicing open defecation than those who didn't get cholera, right? That's really what it means. All right. That's precisely what it means. Okay. All right. So we've talked about this, has soap at home and how you would do the how that's a protective factor, even in multivariable analysis. All right. Maybe you could try to do the odds ratio now. Let's do it. And so I've gone through the study and put in the numbers. Here are the numbers, right? So of those who had cholera, 18 had soap and 36 didn't. And of those who were controlled, 66 had soap and 56 didn't, all right? So just try to do this odds ratio and we'll work it out. Okay.
Okay. That's 0.42. Yeah. 0.42.
Okay, very good, very good. Okay, so that simply it's AD time divided by BC, so 18 times 56 divided by 66 times 36, and you're right. It's the answer is 0.42. All right, is that what you got to? Close to it? You're getting it. Okay, now the interpretation, right? Yeah, yeah. Let's talk about the interpretation.
Oh, the exposure is so convoluted. Let me try this. Those who
Not, just a-
those who had the disease were 0.4 times more likely to not have used soap.
That's right.
because he did not.
That's right. There's many ways to say this, right? But 0.42 can be turned on its head and it can be called 58%, right? You can turn it on its head, right? And so the way I think of it is like people with cholera are 58% less likely to have soap at home for hand washing. Does that make sense? Yeah. Okay. Hand washing with soap protects against cholera, right? That can be your plain language interpretation of that. Yeah. Okay. All right. Good. Okay. All right. Now I said in this slide I've said three more concepts, but actually I've explained these concepts as we went along, I hope. But just to reiterate, a confidence interval is that indicates the level of our level of certainty or uncertainty around a measure of effect, right? And so it's the precision of the odds ratio, right? So not the measure of spread, but the precision of the odds ratio. You know, precision, how precise we are. You know, if we're very precise, the odds ratio will be narrow. If we're imprecise, the odds ratio will be broad, and it still might be significant, but it might be a broad odds ratio, right? Now, like I said, it takes account of sample size. If you've got small studies, you have wide confidence intervals. Typically, large studies, you have narrow confidence intervals for a true effect, right? You can be more confident with a larger study. The point estimate and the confidence intervals are much closer together, right? Now, remember, what it's saying is that a 95% confidence interval means that what you're saying by that is that the true population effect, the true effect, is 95% likely to lie between those 2 points, okay? You know the point estimate, but somewhere between those 2 points is the true number, right? You're 95% confident about that. All right, now I've talked a bit about adjusted odds ratios and how they result from multivariable analysis, comparing several variables against each other, right? One variable against all the others, or several variables against each other. And that does take into account confounding, and it allows, like the value of it, it allows at the end of the day that you can say a minimum number of predictive variables you've identified, right? A relatively small number, right? And in this study where they looked at 10 or 11, they found really 1 or 2 strong risk factors and 1 or 2 strong protective factors. That's all, right, of those, yeah? Okay. Now the p-value, which I've shown before, but like remember the p-value it's not precise, and it's better to use the odds ratio and the 95% confidence intervals, but it tells you whether it's significant. But what it's telling you is the probability that the true population estimate falls outside that 95% confidence intervals. All right, that actually you got it wrong and it's outside. It's the probability. So if the p-value is very, very low, then the probability that you got it wrong is very, very low, right? Whereas if the p-value is more than 0.05, then you've got more than a 5% chance that you actually got it wrong. So therefore, out of convention, we say, well, that's not significant because you might be 5% chance of being wrong. Huh? Does that make sense? You might think 5% is small. You might think 5% is small, right?
Yeah.
But when we're doing research, we want to know how precise we are. All right. Okay. And if you think about it, a p-value of 0.001, what is that? 1 in 1,000.
Yeah.
Likely that you're wrong, that the number is outside those confidence intervals. That's all. Okay. Yeah. All right. So this study found that major risk factors were defecating in the open air. The protective factors were having soap at home. And this adjusted odds ratio found that both were still significant, right? Both were still significant, even with adjusting for all of those other confounding factors, right? Okay, because, yeah, okay, right. I think we talked about that. Lastly, I want to just maybe just cover this issue we talked about yesterday as well, and that was dummy tables, wasn't it, eh? And how you can early on draft up some dummy tables quite early, because in all your studies you'll have a table of baseline characteristics of your population, and you'll have 1 or 2 tables of your outcomes, and you can draft them up early. And you'll see here what I've done is like been very precise about not only the variables, but the metric, right? And because you can look at this table and be under no doubt as to what the metric is, okay? It's not subjective, right? Because remember, let's say male, female, well, that's a ratio. Age in months. Remember I said it's not age, it's age in months. You could do age in years, depends on your population. It could be days if you're looking at neonatal populations. And we've said that the summary statistic is the median and the interquartile range is the measure of spread, yeah? Duration of cough, median, interquartile range. Temperature, greater than 38. Remember, with this, you could say temperature as a continuous variable, or you could say temperature greater than 38. That is like has the fever. And if it was a continuous variable, then probably median would be the right thing. But because actually what you want to know, there might be some children with fever and some children with maybe hypothermia. So the average is in the middle. So it's not telling you much about that population. But if you want to know the proportion or the percentage that actually had fever, that's the way you do it. Make it as a binary variable, yes or no, they had fever, right? Apnea, number, percentage, poor feeding. Again, these are binary characteristics. They either did or they didn't have the variables, right? Then we're getting down to heart rate, again, median. Again, because this is a sick population, it's not a normal general population, right? These were children with severe pneumonia, right? It's a sick population, so you'd expect the heart rate would be a bit higher on average, right? and oxygen saturation. Now, here, what I've done is two ways of looking at the same outcome, right? And they tell you a bit different things, right? So the oxygen saturation, the median, right, will tell you about the whole population. But you might want to know how many were very hypoxic, right? It could be less than 90 or less than 85 or whatever. But the point is, how many were very hypoxic, right? And so that's a number and a percentage, whereas this one's a median and an interquartile range. And that's useful, especially if you're looking, like this study was more about like severe pneumonia and oxygen use and that sort of thing. So you want to be quite detailed in your description of the baseline characteristics as it relates to the particular, like the area of interest. Right? This will be relevant to your study of it. Yeah. Not so much this, the oxygen thing, but there'll be some variables that you want to be a bit more detailed about. Yeah, so you might look at them in two different ways. If it was a study of you know, temperature instability, then you'd probably have like temperature as a continuous variable. You might have proportion that have hypothermia, proportion that have hypothermia. So that could be three ways of looking at temperature. Does that make sense? Yeah. And radiographic signs present number, like that's a binary variable, right? Yes or no? Because sometimes we, you know, yeah, sometimes we think we can be more precise than what we are. And we might think, oh, well, if they've got some radiographic signs will be different to others, isn't it? Because the present radiographic signs, that could mean like bronchopneumonic changes or lobopneumonic changes, or it could mean atelectasis or, you know, an effusion or something like that. It's any radiographic changes, right? Or radiographic changes absent. Well, that should be the inverse of the two. The reason, yeah, that's all. Okay. So I think it's possible for you to make up such dummy tables to describe your population quite early on in your studies. And that really helps you when you're writing up. That really helps you a lot. And also helps you in your analysis, because you know exactly what variables, what columns in your spreadsheet, for example, you want to analyze. And you also you can then look at it and say, does this describe my population in the way that I want to, right? Have I missed any variables that actually I would like to describe in my population? And then you can just add them in. Yeah. Okay. All right. Okay. So today in the first talk, we talked about a bit of background to epidemiology and different types of epidemiology. And we talked about rates and ratios and proportions, and then incidence and prevalence. And today we've talked about different types of studies, and particularly case control studies. And we've talked about odds ratios and 95% confidence intervals and adjusted odds ratios, that sort of thing. All right. Okay. So we've gone from just looking at descriptive studies to some analytical studies. All right. And tomorrow we'll talk a bit more about, in lecture 3, we'll talk about cohort studies, which are different to case control studies. And we'll touch a bit on randomized trials. And if we get time, we'll talk about relative risk. But I really want to describe cohort studies because I think they're quite important. But that's all we'll do for today. Okay. Stop recording. Okay.